All right, so continue here. Now we're going to look at in terms of the magnetic field generated by a circular current loop. Okay, so imagine you have a straight wire. If you bend it, right, you can just create a loop like that, circular loop. And what you can see over there, right, for let's say this picture A, is that magnetic field has kind of like a complicated shape. Okay, so it has magnetic field kind of like looping like this around, on this side, and then, basically clockwise on to the right, on the right side, counterclockwise on the left side, and seems like straight up at the center. But it's technically very consistent because one of the things it does here is everywhere around the wire, right? So you have the current, you can see, right? So the current is going, counterclockwise in this case. And as the current goes counterclockwise, every segment of it generates magnetic field that goes around in a circle, okay? So now, one of the things we can do here is to find the magnetic field for this particular, let's say circular loop. We have to use the second right-hand rule. So the second right-hand rule. And here's the thing, the second right-hand rule, remember, it involves current and magnetic field. That means it has two variables. Use one to find the other one. Now, one of the things we can do here is I showed you how to find the magnetic field if you have a straight wire. That means, let's say here's a current. So what you do here is you use your thumb is in the direction of the current, then you curl your fingers, and one thing you will see here is there's a magnetic field going around, counterclockwise due to this, due to this upward wire, upward current in the wire. Okay, that means if you have a straight current carrying wire, then what you have here is your thumb is the current, you curl your fingers in the direction of the magnetic field. But if you have a circular current loop, it's actually easier to do other way around. So for example, if you have a current that is going counterclockwise, then one thing you can do here is you curl your fingers in the direction of that current, and you can find the direction of the magnetic field inside the loop. So here you can see, right, if you curl your fingers counterclockwise, it shows that magnetic field should be upward. And that's what you have, right? See, inside the loop, magnetic field is upward, okay? And if you have, for example, a loop that is, for example, like other way around, right? So clockwise, right, current. So if the current goes clockwise like this, then if you curl your fingers in the direction of the current, which is this clockwise, you can see, right, your thumb is pointing down. So then magnetic field will be going down inside the, let's say this loop, okay? Because what we want to do here is most of the time find the magnetic field inside the loop, right? Inside this, current carrying loop, okay? Again, this is also consistent, very consistent with the, let's say, bar magnet. You can see, right, magnetic field is kind of like the way it's generated, right? It's very consistent with that as well. So you have the north, right? This becomes north, this becomes south, just like here. This is north, this is south, okay? Because it's not from here, then goes and kind of comes back like that. From north, goes into south, but through the loop, right? Just like inside the magnet, over here, it goes from south to north, right? Because it has to go around it. Magnetic fields, unlike electric fields, they don't have a start point or end point. They always go around in loops. Electric field has a starting point and a termination point. Magnetic fields, they don't. All right. Now, here's then another thing we're going to be considering. And this is now kind of applying two things that we learned. One of the things here is that a wire with the current running through the will generate magnetic field. And then if you for example, think like this. So here you have this wire 2. So I'm going to take wire 2 as my wire of interest. See, you have wire 2, and wire 2 has a current running through that in this direction, right? So, and wire 2 generates magnetic field. All right, so using right-hand rule, I can find the magnetic field all around the wire 2. But let's say I want to know, where is the magnetic field in this region? Basically, let's say above that wire 2, and that region, which is, let's say, below the wire 2, right? So I want to find on those two regions. So using the right-hand rule, then what I can do here is this. My thumb is in the direction of current 2, and I can see that if I'm curling my fingers above the wire 2, magnetic field coming out of the page. And that's what you have here, right? So this B2 is the magnetic field out of the page everywhere above this wire 2, okay? And below the wire 2, magnetic field always going to be then into the page. So this is just magnetic field 2, okay? This is just magnetic field 2. That means I'm only considering magnetic field generated by wire 2. And everywhere above it, the magnetic field is out of the page. Everywhere below the wire 2, magnetic field is into the page. Again, using the right-hand rule, I can figure that out. Now, what I'm going to do next is I'm going to put another wire distance A from that wire 2, which is basically wire 1, right? So I place that wire 1 distance A from the wire 2. Well, here's what I have. Wire 2 generates magnetic field in the region where now wire 1 is, as we already talked about, right? This B2 is already there. So then as soon as I have a current running to the wire 1, what I have here is there's a force acting on wire 1, because wire 1 is in the external magnetic field, which is generated by wire 2, right? And if you have a current running which is perpendicular to the magnetic field, right? Well, at least, it's not parallel to the magnetic field, there's going to be force acting on it, okay? And using the right-hand rule, you should be able to see, right? See your fingers in the direction of the current, then you curl in the direction of the magnetic field, which is out of the page. Then you can see, right, there's a downward toward wire 2 force from the, magnetic field 2, okay? That means what you can think of here is this. We are looking at two concepts here. The magnetic field generated by the wire 2 exerts force on wire 1, okay? That means I'm taking wire 2 as my source, okay? The current 2, right, in wire 2 is my source, which generates magnetic field. And then you can think like then current 1 or wire 1 is my test wire, right? So when I place that in the region of magnetic field, P2, there's going to be force acting on it, okay? And the way you can see, right, this force is basically acting down toward wire 2. Okay, now, one thing I can, so basically this is hopefully clear. So there's also another thing happening exactly at the same time, simultaneously. So here's what I'm going to do. While this is happening, right, I can also have, let me try to get a different color. I can also have this. Well, now wire 1, with the current running through the wire 1, generates a magnetic field of its own, okay? In the entire region, there's now another magnetic field due to the wire 1. Let's see where the direction of the magnetic field due to wire 1. Well, same way, if I use my thumb in the direction of wire 1, I can see everywhere above it, right? Everywhere above it, the current 1, so the current 1 now generates magnetic field 1. So I'm going to call this B1. So anywhere above it, there's out of the page magnetic field. That means, magnetic field above wire 1 becomes even stronger, because now we have magnetic field due to wire 2 plus magnetic field due to wire 1, both in the same direction. So the magnetic field becomes stronger over there. But magnetic field 1 below wire 1 will be curling into the page. That means everywhere below wire 1, like everywhere here, there is a magnetic field into the page. Okay, so this is going to be then B1, right? Now, here's the thing. Wire 2 does not, feel any effect from its own magnetic field. That means whenever it generates a magnetic field, wire 2, when it generates magnetic field, it's unaffected by that magnetic field. But wire 2 right now will be affected by the B1, magnetic field generated by wire 1. Well, because now this B1 is an external magnetic field for wire 2, right? That means as the wire 2 has a current running, let's say to the right, then there's a magnetic field into the page in that region. Now due to the wire 1, there's going to be force acting on wire 2 because of that magnetic field 1. And that direction of the force, using a right-hand rule, you can see, right, fingers in the direction of the, current 2, which is to the right. Then you curl into the page for B1, right, magnetic field 1. Then you'll see your thumb is pointing up, which means that the force acting on wire 2 due to wire 1, let's call this F2, is then upward toward the wire 1. So you can see, right, they both of them exactly at the same time exert force on one another. And that force is, you can see, right, attractive. Both, forces are, pulling those wires toward each other. And that's what you're going to see. So technically, if you have two wires with same direction current, let's say with some finite distance between them, then the force is going to be always attractive. That means they're going to be pulled toward one another. So there's going to be force pulling them toward one another. But if there's a wires, again, with some finite distance A between them, have opposite direction force, then again, you can try to do this, right? Using the right-hand rules, you can see, right? Then there's a force that basically going to be in opposite direction, so it can be repelled, okay? That means wires in the same direction current attract wires with opposite direction current, going to repel each other. All right, so what is then the magnitude of force, for example? Well, remember, this is the equation that we learned. That means, force on a wire due to external magnetic field is current times length times magnetic field, okay? But now we also learned that magnetic field due to a straight wire is this equation, right? Mu naught times the current times 2 pi a, okay? That means what I have here is, see, this is force on wire 1, which is equals to current 1 times length, which is the length of the wire 1 that is exposed to the magnetic field 2, but times magnetic field external, which is then happen to be magnetic field due to wire 2. Well, then I have I1 times L, but then this magnetic field due to wire 2 has the equation, like as we talked about, right? It's mu naught times the current that generates this magnetic field 2, which is, wire, the current 2, divided by 2 pi times the distance, and the distance from the wire 2, which is distance A, that means the distance between wire 2 to wire 1. That means you can see, right, if you combine this, it becomes mu naught, I1, I2, right, times length, divided by 2 pi a. Oh, I'm missing pi over there, so 2 pi a. Okay, that means that's the equation for the force on wire 1, which also equals for the force on wire 2, which, you can do that, for wire, force 2, right, which will be current 2 times magnetic length times magnetic field 1, because force on wire 2 due to this magnetic field 1, which is equals to I2L, and then mu naught I1 over 2 pi a, because this is magnetic field Y due to wire 1 and current 1. And if I combine, you can see that you get the same, equation. So that's why, 1 and 2 are, equal to one another. So that means those wires. All right, so then a lot of times what we do here is we can, okay, so again, so these are the equations, right? So we can, instead of calculating the force, because this length can be given to you or it might not be given to you. So instead of doing that, we can then divide both sides by length and then calculate what we call force per length quantity, okay? So let me show you the equation here. Something like this equation over here, take it and divide it by the length. So you get this force per length, which is equals to mu naught constant times the product of current 1 and 2 divided by 2 pi times the distance between the wires. That means the equation applies to both wires. And when the current are in opposite directions, magnetic forces are reversed and the wires repel each other. Okay. So parallel conductors carrying currents in the same direction attract. Parallel conductors carrying currents in opposite directions repel. Right. So similar things you can think of, like, that same thing can be applied to two loops, right? So if they have the same direction, let's say a current, right? They're going to be, attracting one another. If they have, opposite direction, let's say currents, then they're going to be repelling each other. Okay, so kind of like same thing for the wires and the loops. Okay. Let's look at then the magnetic force between, so basically the magnetic force, by the way, this is what Ampere, one of the discoveries of Ampere. So the magnetic force between two parallel current varying wires is used to define Ampere. Okay, so this is how, that unit of Ampere was defined. So if two long parallel wires, 1 meter apart, carry the same current and force per unit length on each wire is 2 times 10 to the 27 Newton per meter, the current is 1 amp. Okay, so well, I'll double check actually on that value, but that's kind of like how we define, the Ampere. So hopefully that's correct. And same way is the Coulomb can be defined in terms of Ampere. Remember, if conductor carries a steady current of 1 amp, the quantity of charge that flows through a cross section of the conductor in 1 second is 1 Coulomb. Remember, right? The current was, dq dt, okay, which is the rate at which. So in 1 second, 1 Coulomb of charge, as 1 Coulomb of charge, right, goes through that, then, to have 1 Coulomb, we can say that it was 1 Ampere, in 1 second. So sort of like that. All right. So this is experimentally determining the direction of the magnetic field due to a straight wire. So you can see, right, here's our reference experiment where we take a wire and put some magnets or compasses around it. So those are the compass, right? They have magnets, right? The magnetic needle. But you have the compass around the wire, and you can see, right, what they do is just they detect Earth's magnetic field. They're all pointing toward the Earth's magnetic field. As soon as you have a magnetic, as soon as you have a current running through the wire, then this current then generates magnetic field, as we talked about, right? So then you can see, right, it curls, the magnetic field curl around the wire. And then the compass, because it's so close to the source, it basically aligns itself with the direction of the magnetic field generated by the wire. So you can see, right? So now all of them are pointing in this direction. So that's why we know that it's counterclockwise, because that's what the compass does. Compass always aligns, with respect to the direction of the magnetic field. So so let's say if you have a conductor and then you have some iron filings, right? You can see, right, how they're nicely lined up like that. Very similar to basically curl of the magnetic field. And obviously once the current is reversed, so let's say if I have the current going down instead of up, all of the compasses then going to change their orientation. Again, all those needles going to be reversed. All right. Now, hopefully, you guys agreed with me that the Biot-Savart Law was not really a nice way of, solving those problems using the Biot-Savart Law. You usually have to always go with this tiny element and then find the expression and then do the integration. And a lot of times, that can be very tedious, very difficult to work with, and, like a lot of times, when I teach engineering, physics classes, right, we do have to go over those, tedious, let's say difficult derivation and, integrations. But, at the end of the day, one of the things we have here is just like for the electric fields, we can use the Coulomb's law, which again can be very similar, very difficult, let's say derivation. And then we learn there's a Gauss's law, which can use the symmetry to very quickly find the same thing in just a few steps by using the dot product and concept of flux. Same thing we have here for the magnetic fields as well. Okay, that means we can use the symmetry to find magnetic field. So that's why So the Gauss's law, we determined the electric field in a highly symmetric situation, and we're going to find analogous for the magnetic field. Okay, so we're going to find way of determining magnetic field for some, symmetric situations where there's a current in a wire or in a loop and things like that, and we can find, magnetic field using the symmetry to our advantage. All right, so just like that dot product for the Gauss's law, so we're dealing with another dot product, okay? But this is different because the dot product for the Gauss's law was technically two-dimensional, remember? So electric flux was equals to E dot dA. So this was with respect to the area. So here, this is not the magnetic flux actually, right? So this is, just a product, a dot product, which is magnetic field dot ds, which is that length element, okay? So you can see, right, what we have here is we are considering then this particular dot product, okay? So you can see, right, for small length element on the circular path centered on a wire. So let's say you have a wire, could be this, straight wire, right? And what you have here, so for example, here's straight wire. So what you want to do here is, let's say, find the magnetic field at some point P, which is distance R from it. Okay. So then one thing we're going to do here is say, all right, so what I'm going to do here is I'm going to draw some kind of closed loop around that wire of interest, and let's say around my source, right? And this closed loop, basically, I'm going to then integrate this B dot ds around that. Okay, so you can see, right? So we have a small length element on the circular path centered on the wire. That means, one of the things I want to do here is I want to make sure that, I have the same distance R everywhere, right, with respect to this. So that means the wire is exactly at the center of my, circle. Sometimes this is also known as, you can see, right, this is Ampere's law. So this is known as Amperian loop. Okay. And by symmetry, the magnetic field is constant in magnetite on this circle. Okay. That means, again, so let's say, I don't know where to put this wire. So for example, here's my wire. Okay. So if I'm considering this point P, okay, so what I will do here is I will draw my loop. Okay. Just like before, remember Gauss's law, you would just basically, remember, do some kind of shape, spherical shape or cylindrical shape and things like that, and find the electric field for that shape, and then which will then be used to find the electric field for the source itself, right? Because they're related, to the concept of flux. Well, same thing here. So you can say, all right, so what I have here is I'm going to draw a loop like this, right? Circular loop, where I'm going to say that source is exactly at the center of my loop. So let's say some, I don't know, distance R, right? Okay. Now, what I have here is then I'm going to find magnetic field around that, loop. So let's say I'm going to find magnetic field around that loop, which is, I'm doing the, the integral of B dot ds. Is I have to integrate for the, for that entire circle. So B dot ds, and it's a closed integral because it's a closed loop, right? So that the symbol represents it's a closed integral. Okay, so now I have B dot ds. Okay. Now the question here is this: is the magnetic field constant around, this loop, this circular path, right? So if I go through every, let's say position, right here, 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 like let's say I go around this, the circular path, and I want to look at, is the magnetic field constant? Is magnetic field constant? Is it the same as before, and things like that? And if it's yes, if it's constant, and the thing is, we want it to be constant, so we choose a shape, or let's say choose a configuration so it makes the magnetic field constant around that loop. Then I can just remove that from the integral and just have it, just ds. Okay. And what I have here is then the b times integral of ds. Well, integral of ds means that if you start from here, you go around and integrate over around the entire length, which is just nothing but the circumference, right? 2 pi r. Okay, so that's magnetic field times 2 pi r. Now, if you remember, I gave you the equation for the magnetic field, some distance r from a straight wire, and I told you that it's equals to mu naught times the current, so let's say times the current, divided by 2 pi times the distance, right, 2 pi r. And then, so this is just the magnetic field, right? So this is basically just this guy over here, right? Mu naught I over 2 pi r. Then times this, the result from the integral, which is 2 pi times r. Okay. And one thing we can see here is that 2 pi r's cancel out. That means this integral of b dot ds is equals to nothing but what remains, which is constant times the current inside or enclosed in my loop. And this is then what we use as Ampere's loop or Ampere's law, okay? And that's very similar to integral of E dot dA equals Q inside my, Gaussian surface over some constant epsilon naught. So you can see, right, as a format, right, they're very, similar. So I find, some integral and relate to the charges inside, which is usually source, right? And here I find, the integral, around, some circle, right, some path, and relate it to the source inside, which is the let's say the current in this case. All right, so that's what we have. So the general result is Ampere's law, which tells you that anything you have, right, any type of, let's say, wire you have, or, let's say any type of different shape you have, right? So you can create some kind of loop around your source. And it doesn't have to be, let's say, circular, shape. It can be rectangular, it can be circular, right? It can be, let's say, but, pay attention, right? So this is ds, which is, it's a line integral. It's not a surface, it's a line. So it's actually, I get either like, let's say, a circle, or let's say a rectangle or a square, right? So it's a one-dimensional integral rather than like a surface integral. So Gaussian surface could have been, a plane. It could have been a sphere. It could have been, let's say a cylinder. But here we're doing just a line integral. So it's just either a circle, right, or a rectangle, or a cube, and things like that. So, and what we have here is that, let's say, any type of surface that, let's say the loop that you're considering, then you're integrating around that, loop, and that integral E dot ds is equals to mu naught times the current inside your loop. Okay. So now, so let's say, for example, that loop that I have, does it have a, current inside? Well, it doesn't. That means the right side of the equation equals to 0. Well, that means integral of b dot ds equals 0. Is it because the ds is 0? No, ds is just, I have an actual loop and it has a, ds component. Well, it's 0, that means because there is no magnetic field. Okay, there's no magnetic field, that's why it's 0. So that's why we can use this to conclude, technically, is there, current inside your loop or not? If there's a current, that means you might have a magnetic field. What if you have, 2 wires like this, one with the current up, another one with the current down, and this is 10 amps and this is 10 amps. How about now? Well, again, I have net current 0 because, one is up, the other one is down. If I add them together, I get 0. So technically, this is like, let's say, net. So let's say net current. Okay. So, and if the net current is non-zero, you can find the magnetic field. If net current is 0, or there is no current in your loop, then you can have this basically saying that you can conclude that magnetic field is also 0. All right. So Ampere's law is valid only for steady currents. Okay, so it cannot be time varying currents. Even though Ampere's law is true for all current configuration, it is only useful for calculating the magnetic fields of configuration with high degrees of symmetry. Well, because if the symmetry is not high, that means this derivation can be as tedious as Biot-Savart Law. There's really no advantage of us using this equation at all, so let's say. But for the high degree of symmetry, problems, this becomes super useful. You can calculate the same thing, like let's say in only a few steps. All right, so to use Ampere's law, let's summarize this. The path of integration, so we call it again an Amperian loop, must satisfy one or more of this, following. The value of the magnetic field can be argued by symmetry to be constant over the portion of the path. Okay, that means, let's say, if this is my loop, I'm considering that whatever I have the source inside is such that, magnetic field everywhere here is constant. So that's why I can remove that from the integral. The dot product can be expressed as a simple algebraic product B ds. Because remember, B dot ds is equals to B ds cosine theta. But, if they're perpendicular, it can just be B ds. All right, what else? The dot product is 0 because the field and length elements are perpendicular. Again, because of that, as I saw, right? There's a cosine theta, right? So B dot ds is equals to B ds cosine theta. If B and ds are parallel, theta is 0. So this is equals to B ds. If B and ds are perpendicular, theta is 90 and cosine of 90 is 0. So you get 0 dot product. The magnetic field can be argued to be 0 at all points on the portion of the path. Okay. So that means, depending on what you have, right, you can also have that magnetic field, right, can be argued to 0, let's say, if there is no current inside. Again, because you have a loop, it has ds, and if at ds, but it's, the B dot ds, let's say, equals 0, it's because the magnetic field is 0 everywhere, along the portion of that path. All right, so let's look at this, example over here. Because, for example, you might be given some kind of conductor and you want to find the magnetic field inside and outside of the conductor. Using the Biot-Savart Law, it can be relatively tedious. And I would not, do that in this type of class. But using the Ampere's law, it becomes, simple, at least, for the outside. For the inside, you still have to consider, a few things, but it's still, it's relatively simple if you are, using the Ampere's law. Okay, so let's look at this. So you have a long straight wire of radius r, carries a steady current I that is uniformly distributed through the cross section of the wire. That means, there is no portion of the wire that has more current than the other. It's all uniformly distributed. So you want to calculate the magnetic field at distance r from the center of the wire in a region where, this distance r is less than the radius or equal to the radius, right? Or distance r that is greater than the radius. Okay, that means, inside and outside of the conductor, pretty much. Okay. So now, we start with the, the first one, which is r greater than or equals to the radius. Okay, that means I choose. So we can say, right. So this is my Amperian loop for this, case one, which is r greater than or equals to the radius. Okay, so you can say, right. I choose a loop that is concentric to the wire, right? And if I'm looking at from sort of like, let's say, head on, right? So let's say here's a wire. I'll make it a little bit bigger. So let's say here's my wire with the radius r, and then this is my loop. And my loop has a radius r like that. Okay. So now, what I'm going to do here is I'm going to find the closed loop integral of B dot ds for that Amperian loop. But now I know that this will be equal to the mu naught times the current inside my loop. Okay, now first thing is, do I have a current inside my loop? Yes, the wire inside has a current, so the right side is non-zero. That means the next I want to integrate that. The next is, if I'm looking at everywhere on this loop, is the magnetic field constant? It is because it has the same distance from the wire. So that means it is constant. So I can then, oops. What I can do then I can say that, all right, so then magnetic field is constant, so I can remove from the integral and just have BDS. And this is equals to mu naught times I. All right, so then BDS become B. This integral gives me nothing but 2 pi R. And this is equals to mu naught times the current. That means magnetic field, some distance R from that, like some point P here, for example, some point P over here, right, will be equals to mu naught times the I divided by 2 pi R. And that's the equation for the magnetic field that I showed you. But now I'm able to derive it for you because Ampere's law allows me to find the magnetic field for a current carrying conductor. Remember, so here's a wire with the current. Here's point P. What is the current there? What is the magnetic field there? You use this equation. There you go. Because this is, you know, outside of the conductor, and you can find the magnetic field over there. All right. So let's see then part B, or you know, the second part. Let's say case 2. So this is a little bit more complicated compared to the, you know, the case 1. So let's say I want to know what is R that is less than the radius. That means somewhere inside. So let's say maybe like here's my point P, and we're inside the conductor. Well, what I do here is then I use the second Ampere. That means I draw a loop, or you know, such that my loop goes through that point P, right? Because that's, you know, since I'm integrating over that loop, I want that loop to go through that point P. So then when I'm finding magnetic field, I'm also finding a magnetic field at that point P. All right, so then what I have here is this. Closed integral of B dot ds equals mu naught times current inside. All right, so let's look at the left side of the equation. Well, that's the easy one because again, magnetic field everywhere along that loop 2 is constant, so it becomes B ds, and this just becomes B times 2 pi R. Okay, B times 2 pi R. Now then this is equals to then mu naught times current inside. Well, here's where, you know, we have to be careful because this is current inside my loop. That means current in this region, which you can see, right, is not the same as the entire current. So this I is for the current everywhere in this conductor. But current inside my second Amperian loop is only the current through that, you know, loop that I have. That means I want to know what is the fraction of that, you know, the current, right? What is the current inside, right? So I in, which is, you know, for my loop 2, what fraction of that total current it is. Okay, that means I have to try to find that. Now, one thing I have here is this. There's something I can use that is very, you know, easily allow me to, you know, find a relationship between those two currents. Now, regardless of, let's say, which current I'm considering, this, you know, the maximum current, right, this total current, remember, if I take this total current and I divide by the area of the total area of the conductor, so total area of the conductor, what I get here is, remember, current over area, if you remember, was the current density. That's my current density. Current over area. That means total current divided by total area equals current density. Okay. Now, what I'm going to do here next is I'm going to say, okay, so now I'm going to consider this my Amperian loop 2. I'm going to say, all right, so if I take the current through that, so I'm going to use prime for that. That means current through that, right? So here's I prime, then divided by the area of my, you know, loop 2, A prime. Well, if I do this ratio, I'm also going to get same current density because this is just like the density. Remember, if you take 2 pieces of gold, doesn't matter their size or shape, you will going to get same density. Same thing is here, right? So this ratio of the, you know, current over area is always going to be same no matter what part of the conductor I'm considering. Well, that means this ratio is also the same, right? current over area divided by current prime over area prime. Remember, this guy over here is my current prime. So I can rearrange and say then current prime is equals to the ratio of A prime over A times the total current. That means you can see, right, how this guy is related to the total current. Okay. So that means here I have then V times 2 pi R, and this is equals to mu naught, then times this A prime over A times then total current. Right? That means I'm replacing, I prime. You can think like so. So here, so this is I prime, right? So this is I prime. So basically, this is my I prime. Okay, so I'm replacing I prime with A prime over A times the current. Now, what is that? Well, this is mu naught. What is the A prime? Is pi R squared. What is the A? Is pi times the radius square, right? Because, A prime is the area of my loop. A is the area of the conductor. So, and then from here, you can see, right, I can cancel the pi. Then what I end up with this is B times 2 pi R is equals to mu naught times then R squared over the radius square times then the total current. All right. And then from here, so if I can then rearrange, you can see, right, this R cancels with that, right? So that means I have only one R dependability for that, and just rearrange it and basically get this equation. So again, more room here. That means I have B 2 pi R was equals to mu naught R squared over the radius squared times the current. I cancel those, and then I have magnetic field, which will be mu naught times the current divided by 2 pi times the radius square, then R. Okay, so most of the time we kind of rewrite it like this to show that everything in the parenthesis is basically constant. The only thing that can change here, this R, because, for example, if this is my conductor, and let's say this was my loop, so what I have here is this. So this is the center. So as I increase my R, so here, I'm increasing my R, right? As my R increases, you can see, right, B is directly proportional to R. As I'm increasing, it means, let's say, here's my Amperian loop, here's my Amperian loop, here's my Amperian, here's my loop. So I'm increasing, and the B is equivalently increases with the R. That means there's a direct linear proportionality for the magnetic field and the distance from the center. All right. That means this was the equation. This is basically inside the conductor. And this was the equation, right? Mu naught I over 2 pi R. So this was from outside. Okay. So inside and outside. And if I'm doing a graph where this is magnetic field as a function of distance, so you can see, right, as I start from the center of the conductor, as I'm increasing distance, my magnetic field increases according to this equation. So it increases all the way until I reach the radius. As soon as I reach the radius, then I'm going outside of the conductor, then my magnetic field drops as 1 over R. Look, drops 1. 1 over R like that. Okay. So this is B proportional to R. Here's B proportional to 1 over R. So you can see, right? So, and that's according to those, two equations. All right. So one of the important thing about, this chapter is that we're going to talk about solenoids, which is things like this. So you take a loop of wire, and then we know that if there's a current running, right? So if there's a current running, there's going to be a magnetic field. So sort of like something like this. And if I, if I have more, let's say loops, for example, right? Then I can put next one, like let's say put next to one this one. So another one next to this one, another one next to this one, another next, and then I can, make this magnetic field through the, those loops, right, more and more and more uniform. Okay, so again, solenoid is a long wire wound in a form of helix. So basically, if I have this, right, I can wrap more and 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 more, and have a large, let's say, a solenoid with large number of loops. Okay, and what we get here is this. So a reasonable uniform magnetic field can be produced in the space surrounded by the turns of the wire. Okay. Each of the turns can be modeled as a circular loop, and the net magnetic field is the vector sum of all the fields due to all the turns. That means magnetic field can be proportional to the number of turns. More turns you have, greater the value of the magnetic field. All right. So here's an example of a solenoid. You can see, right? It's not just one loop. It's like, you put them together, so then you have, n number of loops. N is the number of loops, so number of turns, okay? And more you put together, more uniform the magnetic field inside that, solenoid. So solenoid is just basically this device, right? So, or configuration. Okay. So if the turns are closely spaced and the solenoid is of finite length, the field lines are as shown in the figure, okay? And you can see, right, it's very similar effect like you might have for the bar magnet. Okay. The field lines diverge from one end and converge at the opposite end. And, exactly same type of behavior that you might see for the bar magnet. So kind of like become like a north region and then, a south pole. So north pole region and south pole region. Okay. Now, imagine like, let's say you come back over here, you take a knife, I don't know, so let's say you take a knife like this, and you cut this thing exactly in half. And you get something like this. So you are, cutting in half, you're looking at, so here is where the current goes into something like this, kind of like goes like this, right? So it goes into the page, coming out of the page, goes into the page, coming out of the page, into the page. It's kind of going like this. The current going like this, and as the current going like that, right? And large number of turns combined together, look at the magnetic field. It gives you a magnetic field that is almost completely uniform inside. Okay, and this again, so the solenoid generally has a really large number of turns. And if you have large number of turns, magnetic field can be considered very uniform and strong inside and very weak outside. Right, so let's summarize, right? So as the length of the solenoid increases, the field within it becomes more and more uniform. And for an ideal solenoid, the turns are closely spaced. The length is much greater than the radius. That means, like, let's say if I'm considering the radius of solenoid, so let's say here's the radius, right? So, and then let's say this is the length. The length of the solenoid is much greater than the radius. The field outside of the solenoid is negligible. Maybe there's some field outside over there, right? So kind of like going like this, right? But they're very weak compared to inside, so we can ignore it. And then the field inside is uniform. And that's a key because you have uniform magnetic field inside the device, very similar to the device that generated uniform electric field. Remember, we call that a capacitor or a parallel plate. And what was the important thing about that? We could store energy in those plates, right? So the same idea will be here that, especially in the next chapters, right, we're going to talk about, you can store magnetic energy in those fields, okay? Anyway, so what if you want to find the magnetic field strength inside the solenoid? Okay, so what you do here is to find the magnetic field inside the solenoid, we basically use Ampere's law. But we have to use a very specific shape here. Because for example, if I use something like this, right? Or something like that, it's not really gonna help me because of the way this particular shape is. The best way to do here is do a rectangular path. Okay, so let's say here's this rectangular path. Okay, where you have basically 4 segments, right? 4 segments. you have then length L and width W. Okay, so you can say, right? So you can say that this is my length L here, right? And then this is the width W. Okay. Now you have segment 1 inside the solenoid, segment 3 outside of the solenoid, and segments 2 and 4 kind of crossing between solenoid and outside. And what you have to do here is you're going to then calculate. You're going to then have to calculate 4 different, let's say the integrals. So this will be, the magnetic field. We kind of go over some of those things and then I'll do the equation. So you can see, right? So we're going to apply the Ampere's law to the path by evaluating the integral over each of the 4 sides of the rectangle. The contribution along the side 3 is 0. That means if I'm looking at this is 0 because the magnetic field lines are perpendicular to the path in this region. All right. So I can just basically ignore that. And the contribution from sides 2 and 4 are both 0 because the field is perpendicular to the length element along these paths. Okay. But the inside and outside, both inside and outside of the solenoid. Okay. So that means if I'm doing the dot product, over here, right, if I'm considering the ds, so this is perpendicular, so this is 0. Here, if I'm considering again ds, this is perpendicular, so this is 0. That means integral through the path 2, integral to the path 4, and path 3, all gonna give me 0, which leaves, path 1 as only integral that, I will consider. So that this path 1 or side 1, if I'm doing the integral, you can see, right, it's just closed loop b dot ds. Okay, so then I'm looking at that, only that side, b dot ds, and I can see, right, this is along that line, magnetic field is constant. So I can remove from the integral, so it becomes integral of ds. Integral of ds is just the length from one end, let's say A, to the other end, which is B. And that's nothing but length L. So my magnetic field here is equal to B times L. All right. That means both, so the right side of the Ampere's law involves a total current that passes through the surface bounded by the integral. Remember that we have this was just the left side of the equation, right? And the right side equals, this is equals to mu naught times the current. Okay, so mu naught times the current. Okay, that means what we have here is that particular Ampere's law, we were able to calculate the left side from here. So we end up B times L, and then the right side mu naught times I. But if there's a multiple number of terms, then you can technically put N over there as well. That means you have then magnetic field is equals to mu naught times N times current, and then divide by this length. And that's the equation for the magnetic field inside the solenoid. Okay, so the total current through the rectangular path equals the current through each turn of the solenoid multiplied by the number of turns enclosed by the path integral. Again, we get B dot ds from this left side of the equation. We ended up with a B times L. Then the right side is mu naught I, but we include N because there's number of turns. And then we derive this equation over here. But then from here, we can see that this term N over L, which is number of turns per unit length, is equals to, remember that N, which is a number, concentration number. So you kind of can use that as well. That means this just represents how many turns per length you have. That means you can say the magnetic field is equals to mu naught times N times I. And this is, you can say, magnetic field of the solenoid. And we always only consider the inside of the solenoid rather than, outside, because outside of the solenoid, we always assume that magnetic field is, negligible. Okay, again, and which is basically number of turns per length can be, you know, replaced, right? Either one of those is okay. So you can leave either the first one or the second version of that, depending, let's say, what you're given. Okay, but either version will be okay. All right, so that's it for this chapter. You know, hopefully you guys will be able to, you know, watch both of the videos and, you know, start working on the homework and do the recitation.